All right, we've got a Simpson's rule question here. The diagram shows a block of land and its dimensions in metres. The block of land is bounded on one side by a river. Measurements are taken perpendicular to the line AB from AB to the river at equal intervals of 50 metres. Okay, straight away my mind's ticking off. We're Simpson's rule. So even if we're Simpson's or trapezoidal, we need to know the height. The height is the difference between any values, any two x values or any two of the intervals there. All right, the intervals are 50 metres apart. H is 50. Okay, well, we really have some decisions to make here. My suggestion was that the easiest way to get these questions right, and according to HSC markers, who gets this question right the most, it's people who go and take multiple applications. So that's what we're going to do. Now that y value there should be 200, by the way. There should be a 0 in between there. It's just been whited out or something or missed by the printer. Okay, so our first application, A1. Of course, the Simpsons have 3 children, so we go H on 3, 50 on 3. Just a quick little aside here. If you are someone who's saying, I would really like to go and do another of the approaches that we have, either using the table or evens and odds, that's fine, you'll get the same answer. And if you don't get the same answer, it's because you've done it wrong. So it should be exactly the same. All right, these three, 210, 220 and 200 are going to be our first application. So it's going to be 210 plus 200 plus 4 lots of 220. Okay, if I go put that in a calculator, I get 21500. So essentially what I found there is this area. Well, what we actually notice is I'm going to have to do the formula 3 times. These are my 3 lots if you'd like. Again, that you might say, so there's so many values there, I'd really like to go and do just a single application of the formula using a table 14241 or odds and evens. Well, that's fine, but this is the way we're going to do it here. In fact, at the end of the video, I might confirm with the table and with the single application that we do get the same answer. Our second area, A2, which is the one in red, let's follow the colour scheme. A2 equals 50 on 3, same height, must be the same height consistently. Outside of, or 200 is my first, 210 is my last, plus 4 lots of 190. If I put that in a calculator, I end up with 19500. Now I've just picked up an error. That should be a 3. The calculation is correct though. Picked it up before I put it in my calculator. So we've got area 1 and area 2. We've got to go find area 3 now in blue. So same approach, area equals H on 3, same height, 50 on 3, outside of 210 plus 240 plus 4 lots of 240. Again, don't be confused by this. The fact that we've got 240 in there twice, just because the height's the same. And we go put all that into a calculator. 23500. So that means our area total equals 23500 plus 21500 plus 19500. All that gives me 64500. It's an area, so metre squared. And if we go back, if you flick back and look at the diagram, what we end up with is the biggest area, which was the one in blue here, is the one with the biggest heights. The smallest area, which was our middle one in red, had the smallest height. So it logically does make sense there. Now I said I would confirm that this worked using the other methods. Well, not the other methods, but the other same Simpson's rule. Exactly the same. I'm really only looking for the values of the function. Well, if I'm going to do the table method to start with, I don't really need x values in the table. The x values don't matter here. I've got the y values, which are just the the actual heights of the function. It's not really a function because it's a river, but it's a practical question. But if you think of it as those function values, those vertical distances, that's what I'm interested in. So I don't really need the x values there, so I'm just going to have the y values and then the weight of them. So it'll be 210, 220, 200, of course that's blanked out again, 190, 210, and 240, and 240. Okay, well I said it was 1, 4, 2, 4, 2, 4, 1. Now we, of course, we go find the product of each of those. The product, and what you'll end up seeing if you look at it is that we're basically doing the exact same thing we just done. Okay, in our first application of the formula last time we went the first plus the last plus 4 times the middle. Now the only difference here is we've got 2 lots of 200, but when we go to the second application of the formula, this one got done again. So it was first plus the last plus 4 times the middle. Same deal if we do it a third time, first plus the last plus 4 times the middle. So really everything has been ticked off. It'll give you the same answer, but I'm doing it to confirm it. So this is 210, 880, 400, 38, and 67, 760, 420, oh what's that, 960, and 240. Well, we just go and add all those up together. So our area is equal to, of course, our height on 3, 50 on 3, multiplied by all of that, which is 3870. Sorry, that is an 8. I'm sorry, I would go underneath that, but I don't have space. And that comes out to be 64500. As I said, it would be exactly the same. The single application of the formula, well, I won't go all the way through it, but this is what it ends up being. 50 on 3, h over 3, first, which was, oh, remind me, I think it was 210, plus 240. Now, we need to go and multiply 4 times the odd scores. Our odd scores end up being 220, 190, and 240. They're the same ones in the table that get multiplied by 4. 14241 or 1424241 plus 2 times the even scores, which are 200 and 210. Look, you can go plug all that into your calculator and confirm that it does end up being correct. It does. It's exactly the same thing, as I've said a few times. I hope this has helped. Make your choice about which way you're going to approach this. It doesn't really matter on the type of question how you approach it. If it's a Simpson's rule, as I said, multiple applications of the formula is what will be given to you on that reference sheet, and it's my suggestion of how to do it, but it's your call.